We'll now compute parametric value at risk using a normal distribution assumption and then directly compare it to the historical VaR we computed earlier. Parametric VaR assumes that returns follow a normal distribution, fully characterized by the sample mean and volatility. Under this assumption, downside risk is determined by how many standard deviations into the left tail we move based on the chosen confidence level. This makes parametric VaR simple and also computationally efficient, but also heavily dependent on the validity of the normality assumption. Looking at the table on screen, we see the parametric VaR estimates expressed in return space. At the 95% confidence level, the parametric VaR is approximately minus 1.73%. At the 99% confidence level, the VaR deepens to about minus 2.46%, reflecting the more extreme tail quantile. As before, these values are negative by construction since we are explicitly measuring downside risk. Now, let's move on to the comparison table, because this is where things become particularly interesting. At the 95% confidence level, historical VaR is approximately minus 1.65%, while parametric VaR is slightly more conservative at minus 1.73%. So at this confidence level, the normal model actually predicts a slightly larger loss than what we observe empirically. However, at the 99% confidence level, the relationship reverses. Historical VaR drops to roughly minus 3.08%, while parametric VaR remains around minus 2.46%. This gap highlights a key limitation of the normality assumption. Extreme losses occur more frequently in the data than the normal model predicts. The normal distribution assigns relatively low probability to extreme tail events. As a result, parametric VaR tends to underestimate risk at very high confidence levels when return distributions exhibit fat tails. This is exactly what we're seeing here. At moderate confidence levels, parametric VaR can look reasonable or even conservative. But as we move further into the tail, historical VaR captures losses that the normal model smoothes away. In practice, this comparison is extremely valuable. It shows why many institutions use parametric VaR for reporting and monitoring, but rely on additional measures such as tail risk and stress testing to understand extreme downside exposure. VaR is, without any question, useful, but it is not sufficient on its own. In the next section, we'll formally evaluate how well these VaR models perform by backtesting them against realized returns. This will allow us to quantify how often actual losses exceed the predicted VaR thresholds.